Any questions? So actually, folks, let me make your role a little bit easier. The homework will not be due Friday, because I know you all are probably still working on it, and there's no big hurry at this point. And I am not going to be here Friday, but Todd's going to take the class. I think I'm going to have him talk to you about finite fields, which is the section after. So the section after what we're going to do now, which we'll finish up and we'll make it started on. I'm not letting Todd have that because it's just too much fun. I'm going to make him do finite fields. He'll probably talk to you about that, and I think we'll probably finish that up probably on Friday when I'm gone. Obviously, I've got to travel to Philadelphia, and I won't have office hours, but I should be. I'm probably not going to bring my computer either, but I'll have my phone. So if you're in a spot, just send me a text or an email, and I'll see what I can do. Okay, so theorem. So let's get kind of started here. Let F be an algebraic extension of K. So I've got some notation here. S is the set of elements F that are separable. Oh, yeah. Good idea, John. There you go. S the set of elements of F that are separable. That are separable over K. And P the set of elements of F that are purely inseparable. Both of these are subfields. So both of these are fields that are intermediate between K and F. They're in general not comparable to each other, but they're intermediate fields. That's easy to check. Number one, S is separable over K. That's a separable field extension. F is purely inseparable over S. P is, you guessed it, purely inseparable over K. And let's see, 4. Actually, we saw this one last time, because the elements that are purely inseparable and also separable are exactly the ground field. 5 F is separable over P if and only if F is SP. So that is to say, if F is if all of F is generated by S union P, then F is separable over P. If F is normal over K, let me remind you what that means is if you have an irreducible polynomial Kx that has a root in F, then all the roots of that polynomial are in F. Then S is Galois. So yeah, so perhaps at this point before I finish this evening. So here, this extension here is separable. This is purely inseparable. This is purely inseparable. And this is, if F is S union P, then this extension right here is separable. And if F is normal over K, then what that means is this field right here is Galois, because this field will also be normal and separable, which is equivalent to Galois. If F is normal, so let me finish my thought on number 6. If F is normal over K, then S is Galois over K. F is Galois over P. So what we can glean from that is if F is normal and this condition holds, and ought KS, well, I'll do this. Galois group of S over K is isomorphic to the Galois group of F over P, which is isomorphic to the Galois group of F over K. I'm going to leave this. Like I said, I want to get through this section and just kind of expose you to this. All this is an exercise. Let me give you a corollary to this. So in this one, let me point out separability is transitive. That is, if F is separable over E and E is separable over K, then F is separable over K. And you can get that from the previous result. And here's another corollary. Okay. K be of characteristic P. And F an algebraic extension. Then U is separable over K if and only if KU is equal to KUT. So this is one way to tell a known is separable or not if the extension KU and KUP coincide. Let me point out, of course, you always get this is contained in that. But if you get equality, that means it uses a separable element. I'm not going to prove this in either because I think I've got that as an upcoming homework. Okay. So definition. So this definition, it might help to kind of keep this diagram that I've got over here on the right in mind. Let F be an algebraic extension of K. And we'll say that S is the largest subfield. Subfield of F that is separable over K. The degree so what you have here is, I guess we're still concentrating on this right now. This extension, this is, say, the largest separable intermediate extension between, well, inseparable over K. This is called the separable degree of F over K. Right, so it's just the degree of the biggest intermediate extension that's separable. And so this is not something I can prove. This is a notation, right? So sometimes you call the separable degree F over K is F colon K, so the S for separable. And how do you suppose that you would, I mean, along the lines of this, how would you define the inseparable degree? And what do you suppose is the appropriate way to define this? The degree of, yeah. The problem is this is not always exactly what you want, because remember, this one's a little bit wishy-washy, right? Because this extension right here is not always separable. You need this times this to equal this to be separable. So what we're going to do is we're going to finish our thought here. It's F over S. Notice that here's kind of the clue, I think, that this is sort of the way to go. Because notice that the degree of F over K is the degree of F over S times S over K. Right? Which is, in our new notation, this is FK separable, and this is, oh no, this is inseparable, and this is F separable. Let me also point out, and I'll leave this also as an exercise. So in other words, the total degree of the extension is the product of, and I think philosophically, I think you would want it that way, that the total degree of the extension is the product of the inseparability times the separability. Notice that these two are always positive. So for example, if the field itself, if F is separable over K, then these two are equal. And the inseparable degree would be 1. Right? Proposition. suppose I've got some fields like this, then both the separable degree and the inseparable degree are multiplicative. That is to say. This is actually not hard to prove. Okay, let me give you something that I think is probably not too surprising that we'll use later, and then we're going to conclude with one of my favorites, primitive element theorem. Proposition 84410. Let F be an irreducible monic polynomial. Yeah, I'm going to make this monic here over K. Now I'm going to, since it's polynomial field, I'm going to make it monic just to make my terminology easier. Irreducible monic polynomial over K, F is splitting field. For F over K. And U1 a root number one, and this is kind of cool, every root of f of x has multiplicity inseparable. Right. So what you do is you take KU1 over K, write this extension, and it's not this degree, it's the inseparability degree. So if the polynomial is separable, then this would be 1. So after that, let's see, how do I number the roots? So f of x equals so in the splitting field, we have all the roots, right? So it should be x minus u1, x minus u2, x minus un, but they all have the same multiplicity here. And the multiplicity is the inseparability degree of the extension. So again, if this is a separable extension in KU1 over K, By the way, can somebody explain why all the roots should have to have the same multiplicity? I mean, that does seem like, I mean, it's really great. Right? They all have the same multiplicity, but why can't some of them have multiplicity 2? Some of them have multiplicity 5, like this. Remember, if you have 2 roots of a polynomial, shouldn't you get an automorphism in the field? Where you take, for example, U1 to U2? And shouldn't that also mean that the polynomial, they should be symmetric with respect to their multiplicity, right? Because there's an automorphism in the field. And so basically, KU1 is isomorphic to KU2, for example. So they should share the same multiplicity across the board. That's another kind of nice consequence of the Galois theory. In the number of roots, and this probably shouldn't be a surprise either, is the the separable degree of KU1. Right. So again, for example, in characteristic 0, this will be 1. So all the roots will be distinct, and the separability degree will be right. The separability degree would be just the entire degree of that extension. And here, let me also point out, all the UIs here are distinct. Otherwise, I would have numbered them different. And notice too, if you look at any one of these roots and you take it to the appropriate power, should be the inseparable degree. So remember, this is like that theorem we had before, where you can take an appropriately high power of this, and you can flush it out. Notice that this this should mean that this should be a prime power, right? So anyway, so that is the general theory of how things come apart in a splitting field when you don't necessarily have separability on your side. Okay. One final theorem, but first, any questions? I'm going to go through the proof of this final one. I really dig this theorem. Theorem. This is often called primitive element. And let me kind of motivate it here. Let me motivate this here as follows. Look at this extension here. Anybody want to venture a guess as to how big this extension is, what the degree of this one is? I'm asking you all for an answer. Right, how about 4, right? And this might be a good exercise to kind of this doesn't quite follow from a homework exercise, because one of the homework exercises we had is if you have this is degree m, this is degree n, and m and n are relatively prime, then the degree of the total extension is the multiple of this. It wasn't an if and only if, and in this case, and in fact, we can sort of see it here. I can argue this probably pretty flippantly because notice it's clear, isn't it, that the degree is no more than 4, right? Because certainly if I join the square root of 3 here, that's degree 2, no problem. And if I join this to here, that's a degree 2. So if I join the square root of 2 to this, then the degree of the extension has to be either 2 or 1. And so you just got to ask yourself this. You got to say self is the square root of 2 in this, right? And you can actually get on your bulldozer and write down what an element of this looks like and prove there's nothing in there that will square to 2, right? If you wanted to. Now, it turns out that this is actually a simple extension. It's just I haven't picked the elements well here. It turns out this extension is the same thing as Q adjoint with radical 2 plus radical, right? Let me justify that a little bit. Let me point out that certainly we have that containment, right? Because in this we've got radical 2, and in this we've got radical 3. So this thing contains that sum, so it must contain this. The question is it big enough, right? Now, again, you could get on your horse and try to figure out, okay, is there some way I can write radical 2 as what's the basis of this? Let me point out that I'm gonna show these are equal. I'm going to show that this has degree 4. Right, and so it must contain this, right? And basically, basis here is 1 radical 2 plus radical 3, and now you can square this, right? And if you square this, you get like 5 plus 2 radical 6. I reckon, right? And then you cube this, right? And so really what you get, I want to try to be quicker just to, yeah, whatever. So if you multiply this out, so forgive me because I'm doing this on the fly, but let me multiply that out. So I get 5 radical 2 plus, let's see, that's going to be 2 radical 12, which is 4 radical 3. Right, okay, on that. Then I'm going to get plus 5 radical 3. And then I'm going to get like 2 radical 18, which is 6 radical 3. And so there's too many radical 3s here. 5 radical 3. Oh, yeah, that's right. Right, that's 18. Check that out. There we go. So what I get is like 11 radical 2 plus 9 radical 3. Right, and really, all you need to do is now show that this is a linearly independent set of Q. Right. So I wonder if that's worth our while. So I claim that this is a linearly independent set. So suppose A plus B radical 2 plus radical 3 plus C 5 plus 2 radical 6 plus D times 11 radical 2 plus 9 radical 3 is equal to 0. Right? And I'm praying here very fervently that this turns out to imply that all the constants are 0. Well, so here's what we'll do. What are the integer multiples? Well, let's see, you've got A plus zero, right? Because those are the only, I shouldn't say integers, those are the only rational ones. A plus 5 is 0. Now let's do the radical 2 coefficients. I've got B plus D is 0. Let's do the radical 3 coefficients. I've got B plus 9D equals 0. Oh yeah, it's gonna work out famously for me. And oh yeah, that was
Wouldn't it be 11D plus 11D?
Oh yeah.
Or two.
Yeah, you ruined my day a little bit, but that's okay. It's still gonna work out good. Yeah, it is 11D. And I love this last one. That's an equation even old Jim can solve, right? Because that's the only radical 6 one. And then now you get this huge cascade because now this means that A and C are 0, right? And now these two right here, if you subtract these equations, you get 2D equals 0. So D equals 0, and once D equals 0, D equals 0. So it's a basis, right? That means that when you adjoin this nasty element here, you get a degree 4 extension, which means it has to contain this, and so you've got equality. And you can do this an amazing number of times. In fact, in characteristic 0, you can go bananas over it. So let me be precise here. Let F over K be a finite extension. Yeah, I mean, actually, better be finite, because if it's infinite, then it can't be primitive if you've got it. Yeah, so if it's algebraic and it's infinite, it can't be generated by a single element, right? Because that single element has to have some finite degree, so it's possible. And so if it's not finite, the only way it could ever be a primitive, have a primitive element there, is if it can be transcendental and small transcendental too. If F is separable over K, then F is a simple extension. If F is simple, or F is a simple extension, if and only if there are only finitely many intermediate extensions. How does that Okay, so let's prove this actually. So we prove this in the case that F is a finite dimensional separable extension. So suppose that F is finite dimensional and separable. Okay. Does anybody know? Todd's going to talk about this. It feels like it. Anybody know why we might as well assume K is infinite? let's suppose the case finite, shall we? So suppose K is finite, and then F is a finite dimensional extension. F also has to be finite. Agree? Right? Because it's a finite dimensional extension. So it's a finite dimensional vector space or a finite field. Only got finitely many things in it, right? What do you know about multiplicative? What do you know about a finite subgroup of multiplicative group of the field? It's cyclic, right? And so in this case, F is a finite field. It's cyclic. The primitive element is whatever the generator of that group is, whatever the generator of multiplicative group. So it's, in the finite case, this is true. And in fact, it's easier. So we might as well assume the K is an empty field. So let F so let F bar be the normal closure of F. So in other words, if there are irreducible polynomials in K that, so if there are irreducible polynomials in K that don't contain all roots, then throw all the rest of the roots in. Make sure that F bar is a splitting field. This is again finite, right? Because the splitting field is again a finite extension. So no problem there. So F bar is a finite L1 extension of K. So there are only because the Galois group is a finite group, the group of automorphisms is a finite group, and so there's only finitely many subgroups of the Galois group, and hence only finitely many fields, intermediate fields between K and F bar, and of course that means that there are only finitely many fields between K and F. What we want to do is we're going to choose U and F such that right. I mean, certainly we can do that because the degree of F over K is finite. So I can surely choose some element such that this degree is maximal. And of course, let me point out if F is equal to K, we're done. If not, so I guess we need to investigate that case. If not, we can find some element that's in F but not in K. U, we'll call it V. Then here's V and F. It's not in K. And what we want to do is consider all intermediate extensions form KU plus AV. for example, u plus 0v, u plus 1v, u minus v. Just let A range through all the elements of K. And notice there's infinitely many of those. So as K is infinite, there are infinitely many A plus V, I'm sorry, U plus AV, but only finitely many intermediate extensions. And so that allows us to do a little pigeonholing. So there are A and B distinct elements plus AV is equal to K of U plus BV. So what does this mean? So let's do a little computation here. So notice that A minus BP plus AB minus U plus BB which is in K AB. Since A is not equal to B, B is in, because we have something in K times B is in this, but this thing is a non-zero element, so it's invertible, and of course it's a non-zero element K, so B is in here. U, which is U plus AB plus negative A times B is in K and U plus. And so what do we get from this? So we know that K plus AB contains U and B. So contains A and B. Strictly contains, right? Because remember, V was assumed to not be in K and U. This is a contradiction, as K U had maximum degree among simple extensions. So there's your primitive element. This one that has maximal degree actually generates everything you want. This is really kind of nifty, I think, because, for example, has got one group. That's fine. Suppose it says Galois group S5, and I'm here to tell you they're all over the place. Then what actually has to happen is the splitting field is obtained by this. Let's say the roots are U1, U2, U3, U4, and U5. Then you obtain a splitting field this way. And this degree here is 5. This is degree 4. Three. This is degree 2. And this will also contain the last root. By the way, how do I know it contains the last root? Right, notice how at the end there I kind of I clumped in U4 and U5 at the same time. That's essentially it, because notice that in this case, notice the product of the roots is -8. Right? That means any field that contains the rationals in the first 4 roots automatically contains this root as well. Right? Because this root is just this integer divided by the product of the first 4 roots. But this is a rather complex mess. And the entire degree is 120. So you got to go 120. It's huge. It's got a base of 120 elements. You can find a primitive element for this. That is, you can find a single element in there that generates this. And by the way, if I found a primitive element for this, what's the degree of its irreducible polynomial? 120, right? So this will automatically, I got this from getting a polynomial, a splitting field of a polynomial of degree 5 that had a terribly horrible Galois group. But what you're going to get is the primitive element will be a root of an irreducible polynomial of degree 120. You're going to think, oh my gosh, how do you get its splitting field? Now you've got to go 120 factorial. No, you don't, because this field is normal in the cube. And the primitive element is a root of that 120 degree polynomial. So that 120 degree polynomial, even though it's irreducible, will factor down into linears in this field, right? Yeah, and in fact, I can tell you what the roots are. The roots are u squared, u cubed, like that, would be the powers of that. No, that'll be places. I don't know. I don't know. Yeah, I don't necessarily know that. I retract that statement. Okay, any questions on that? Okay, so Todd is next time going to talk to you, I think, about finite fields, and I'm going to talk to you about approaches for at least for some small polynomials, how you find the Galois, stuff like that. So I get to have the fun, but that won't be till Monday. So I won't see you, but Todd will on Friday. Any questions? Okay, we will see you all when I get back.